So we are moving forward with the sensitivity analysis, and basically it's important that I remember to you, to all of you, that the context is taking a decision in the presence of uncertainty. And it means that when we use, for instance, a benefit function, as I already clarified to you in my introduction last week, it means that the parameters of the benefit function, and in this case A, B, C, and D, are not defined with certainty, but there is uncertainty in their definition. And in particular, I referred, and I will continue to refer, to a case, which is a simple case, for the sake of teaching the concepts. I'm adopting a simple case. I make reference to a case where these parameters are affected by uncertainty. Why? Because I don't have a precise and deterministic vector for A, B, C, and D, but I have three vectors which may occur. It means that basically, this is later, and but in any case, this is the uncertainty. It's given by the fact that there are three possibilities for this vector of parameters. And therefore, if you don't have a unique value, but rather you have, in this case, three possible vectors, the question is, how should I take my decision? And then, I said that one possibility is to check what happens if you take let's say, best estimate for the parameters, which may be the average, and then let's see what happens if we perturb them, if we change them. And I already clarified that I refer to a situation. This is the case I refer to, and these are the expected values of the parameters, okay? 60, 0.08, 1, and 0.7. This is the best estimate, the average, let me say, expected value, which leads to a maximum for an allocation x equal to 38. Okay, perfect. Now, let's see what happens if we perturb these parameters. The perturbation that I assumed is 25%. I anticipate that a key question here is how big should be the perturbation? What is the order of magnitude of the perturbation? Because here I assume that the perturbation is 25%. So this is a first question, which is very relevant. Because the procedure in itself, as I said to you, it's simple. You change the parameters according to the assigned perturbation. You compute the new allocation and the new benefit. And keep in mind that you end up with a different allocation and a different estimate of the benefit. And there are two errors here, the error in the allocation and the error in the estimation of the benefit. Okay? Because let's see, for instance, in this case where I perturb A 25% higher. Okay, so given that this is not the true value of A, the true value is my best estimate. What I assume to be the true value for me is the best estimate, okay? So now I perturb the allocation and I end up with a different, I perturb A and I end up with a different allocation. So there is a mistake in the allocation. This is fine, and it's easily understandable. But then, let's look at the estimate for the benefit. The estimate of the benefit is wrong. But it's wrong not only because a different allocation is used. It's wrong for two reasons. First, because we use a different allocation which is wrong. And second, because the formula for estimating the benefit is wrong. Because A is perturbed. So with respect to the situation where non-perturbation is introduced, I have a mistake in the allocation and a mistake in the benefit, which is composed by two mistakes interacting each other. Okay, then I make these computations, and the conclusion which I reached last week was that we can see from this table that some parameters, their values, are effective on the allocation, so on the first mistake that I make, but less effective on the benefit. So the second mistake is not so huge. Conversely, there are other parameters which lead to very similar allocation, but a different benefit. So assessing the sensitivity means that I'm trying to assess how much sensible the allocation and my estimate for the benefit are with respect to each given source of uncertainty, each given, in this case, parameter. So this, as I said, is quite easily understandable. The problem is, what is the order of magnitude of this perturbation? And this is an evaluation that you have to make, trying to assess the uncertainty of each parameter. In this case, I adopted a 25% for all of them. This is not really credible in practice. In practice, I may know that A is estimated with a good accuracy. What is A? You may remember that A, if you look at this, this graph here, what is A? And let me see, the value of A is 60. A, basically, is around the maximum value of the benefit that you may take. There is the cost. A, if we neglected the cost, would be the maximum value of the benefit. If you look at this function here, and you neglect the cost, for x tending to infinity, the benefit tends to A. So A is an indication of the maximum benefit. And if you introduce the cost, of course, A is still an upper value for the benefit, which, if the cost is reduced, is the maximum. If the cost is significant, is a larger estimate for the maximum benefit. But the order of magnitude of A is the largest benefit. So you may have enough information to quantify A with good accuracy, because you may have enough information to quantify the maximum benefit that you can retrieve from a water allocation. For instance, if the water allocation is given for cultivating a crop, and you know the selling price of the production of that crop, then you can make an estimate of how much money you can take from that crop, which is, if you neglect the costs, the maximum benefit that you can take from irrigating the crop. So this could be an information that you know with sufficient precision. And in this case, it means that you should keep the perturbation of A limited. Conversely, you may assess that the estimation of the costs is affected by more uncertainty. And therefore, the two related parameters, C and D, I go back to the analytical form of the equation. The parameters related to the cost are C and D. If you have more uncertainty in the definition of these parameters, your perturbation should be higher. And again, it's the information that you can collect about the specific case study that leads you to estimate what is the ideal perturbation that you should use. Okay, so let's go back to this table. At this stage, I would like to introduce to you three indexes that are used in this kind of sensitivity analysis in economics. Three indexes that are used to quantify the sensitivity. And in order to understand these indexes, it's extremely important that you remember the mention that I made to the two mistakes and the fact that the second mistake is given by two errors: allocation wrong and parameters that are wrong. So let's assume then that we make reference to our situation where I have no perturbations. And now the purpose is to quantify the magnitude of these mistakes that I made when I introduced the perturbations. So I have a situation which I assume to be the true one, the correct one, no perturbation. Let's introduce these three indexes to quantify the impact of the perturbation. And in order to introduce these indexes, let me introduce first some symbols that I will use. First of all, X star is the optimal allocation with correct parameters, with no perturbation. So it was equal to 38 for the example that I'm now talking about. So X star, again, you see that this is max benefit with optimal decision. Optimal decision is the correct one, and the correct parameters. So I indicate with W the vector, unperturbed vector of the parameters. Perfect. Now, when I introduce a perturbed vector of parameters, I call it W prime. This is, again, the perturbed vector. And X prime is the resulting wrong allocation. You see that here the benefit is affected by the two errors that I mentioned before. Allocation with the prime, which means wrong allocation. Parameters with the prime, which means wrong parameters. Now, once that we computed this benefit for wrong allocation and wrong parameters, we can also compute the benefit by eliminating the error on the parameters. So we use, for computing the benefit, the wrong allocation, but the correct parameter values, which is important. I will show you why. Because this is, if we assume that the unperturbed situation is the actual one, the real one, this is the benefit that I actually take. So this is the benefit that I estimate to take with the wrong parameters. And B X prime W1, W prime, is my estimate of the benefit that I would take by using the wrong parameters. But actually, I take this benefit. So basically, this computation tells me that I'm going to allocate X prime, and my assessment is that if I allocate X prime, I take a benefit of maybe 60, which I compute with the wrong value of parameters. But what happens in practice is that I allocate X prime, and the benefit that I take is the last one, what I actually take, which should be computed with the correct value of the parameters. And indeed, this is, allows us to quantify what is the impact of my wrong decision in my pocket. Okay, now let's introduce these three indexes. Sorry. This is again the table that I it's an extension of the table that I showed you before. For each perturbation, you see the optimal allocation, you see the benefit that I computed. So up to here, it is the table that you have seen before. Here I added this column, is the benefit that I actually take with the wrong allocation and correct parameters. And you see that indeed there is, for some perturbation, there is a big difference. So for instance, let's look at the parameter B. You see that I don't make a huge estimation error. I estimate to take 46 as income. Instead, I will take 44 in practice, actually. It's not a big mistake in the evaluation. Conversely, you see that the allocation changes a bit. But if you look, for instance, at D, you see that the difference between the benefit that I estimate to take and what I actually take is quite substantial. And this may be a problem if you if you applied for a loan from a bank, for instance, and you estimate that you will take a benefit of 51, and what you take in practice is much lower, 20% lower, you may have problems in extinguishing the loan. Okay, so these are the three coefficients, three indexes that I mentioned to you before. Let me say, before explaining them, they are quite straightforward, but they are not easy to remember, and we should make an effort trying to remember them by memory. You should make the effort, but myself too, because this is something, of course, if I ask a question to the exams, I am supposed to know the answer. So this is something that I may ask at the exam, especially if you see that you took indeed some time to study. And so I would like to give to you some suggestions on how to more easily remember them. For instance, let's see that they are expressed in percentage terms. So you have a 100 for each of them as a multiplier. And then look at the fact that the denominator is the same for the three of them. And the denominator is the benefit computed with everything correct. Allocation and parameters. And this is used to make the computation adimensional. So the denominator is the same. So the first one, what is the first one? It's the loss in economic efficiency. What you see at the numerator is the difference between the correct benefit, correct parameters, and correct allocation minus the benefit computed with the wrong allocation but correct parameters. Why this is called loss in economic efficiency? Because, first of all, the numerator is always positive. So it's indeed a loss. Why it's always positive? Because if x star is the optimal allocation according to the parameter vector W, of course, if it is the optimal allocation, it means that it gives the highest benefit. If you change the allocation from x star to an x prime that is different, then you get a decrease in benefit. So the numerator is always positive. Perfect. And this is indeed a loss because after your perturbation, you end up with a different allocation, and then you end up with a lower benefit. So in any case, if you assume that the unperturbed parameter vector is the correct one, with the perturbation, you end up with a loss in economical benefit, which is computed, as you see up there. And then there is an estimation error of the maximum benefit, because you estimate to take this benefit given by x prime and w prime. You estimate to get it, while the benefit that you take is given by, again, the maximum benefit, the maximum benefit that you may take from this allocation is given by mbx star w. So you think that your maximum benefit is given by mbx prime w prime. You estimate it, but indeed the maximum benefit that you may take is given by mbx star w. This difference may be positive or negative. You may overestimate the maximum benefit, or you may underestimate it. And this is an estimation error. Okay, and then there is one more index that can be computed. Because be careful, this refers to your computation and the optimal situation that you may take. Now there is a third computation that you can make, and you refer again to your computation. So wrong allocation and wrong parameters, this is what you compute. But then what you actually take after your wrong allocation is given by NB x prime W. So basically, if you take this difference, which can be positive or negative, you make an estimation error of the real benefit that you are going to take. So there is an estimation error of the maximum benefit and an estimation error of the real benefit that you may take. So, from an economic point of view, as I said, these are the indexes that are used in sensitivity analysis in economics. So, on the one hand, the loss in economic efficiency, and on the other hand, the estimation error of the real benefit and the maximum benefit. And this is a first conclusion. So this is sensitivity analysis. And the sensitivity analysis quantifies what is, again, I'm saying again, the effect of uncertainty on your decision in terms of allocation, in this case, and economical benefit. And this is indeed very useful because, as I said, given that for reducing the uncertainty you need to invest resources because you need to get more information, it's useful for you to know where these increased resources should be allocated. Should they be allocated to reduce the uncertainty in A or in B, C, or D? Sensitivity analysis may help us in making this assessment. But still, this is something that is useful, but doesn't tell us how should we decide. So basically, okay, you now know what is the effect of uncertainty over your decision, what is the effect on your estimates, but you have to move another step forward. You have to decide, you have to take your decision. And this sensitivity analysis tells us the impact of a wrong decision. It doesn't tell you how you should decide. And of course you may say, but this is up to me. I mean, once that you know the effect of uncertainty, and you know what is the possible outcome of your decision, also in terms of errors that you make, you may say, it's up to me. If I'm willing to take a risk, then I may decide in some ways. If I want to be cautious, I decide in another way. So you may say, this is up to me. Once that I know the impact of uncertainty, then you may say, it's up to me as a technician, as a professional engineer, basing on my perception, my attitude to risk, you may say it's my decision then to decide whether I should take the risk or not. But indeed, this is a limited reasoning because it's not just your decision. You have to convince people that your perception, your feeling is correct. And you know, the attitude to take a risk or not is subjective. So you may be willing to suggest to your client, for instance, your farmer, you may be willing to suggest to take a risk. You may say, look, start by irrigating your crops a lot, because I'm quite sure that there will be enough water for the whole summer in the dam, in the reservoir. But then if you get less rainfall than expected, you may end up in August that you don't have enough water. So the farmer may say, I prefer to be cautious, and then you may say, believe to me, you should take the risk, but the farmer may not be convinced. Indeed, even for the attitude to take a risk, we should find an objective way to quantify it. And this sensitivity analysis doesn't tell you any indication on that. It tells you what are the risks, but in decision making, in the presence of uncertainty, you also need an aid, a support, to translate into a decision your attitude to take a risk. A quantitative way, because in this way you may convince the farmer better, like if you agree a method for accounting for the propensity to take a risk, and the farmer agrees on the method, then your decision is supported by a principle that the farmer agreed. If you take your decision just basing on your feeling, you don't have any principle to support it. So basically what we need now is something that takes into account in a quantitative way our attitude to risk. I forgot to show you the final table with the 3 indexes. Just a mere computation. You see that the first one is always positive. I see a -1 and I don't understand why. Let me see. 125D. Let me see what is the benefit. I go back to the numbers because I told you the first one should be always positive. It's a lose in economic efficiency. So it's the negative number doesn't convince me. I go back to the previous table because let me see. NB X prime. Let me go back to the previous table with the maximum benefit. Oops, sorry. 3520. And the maximum is okay, so I just PEE. There is indeed a mistake here. It's a computation error here. And I show you why. Because if we look at this index, PEE, it should be equal to, let's go back. PEE is equal to NB X star W minus NB X prime W. And I should look now at these two values. For the perturbation, the two values NB X star W and NB X prime W, for the perturbation 1.25D. And basically, if you look at the table, you see that the NB X prime W is 4272, is this one, and NB X star W is 44, so the difference is positive. The difference is positive is about 2, and therefore the result here is wrongly reported. It should be 2. I think it's 2 over 24 over 44. So it's 0. Yeah, this is not correct. I should make a computation with the computer, but let's forget it. So the first column should be always positive, while the other two columns positive and negative. Okay, so I said that now we need a method for taking a decision and for accounting for our propensity or reluctancy to take a risk. So, what is a criteria that we could take in order to decide when uncertainty is present? For instance, we may take the decision that leads us to getting the maximum of the minimum benefit. And this is called the criteria of the maximum of the minimum. Let me explain how it works. Let's suppose, as I said before, that you have three possible vector of parameters for this benefit function. So you have parameter W1, parameter W2, and parameter W3. And these lead to three different allocations, optimal allocation, x1, x2, x3. Now, if you, this is, as I said, a simplified situation. So, it means that one of these three outcomes is correct, but it's either, it's just one of these three, okay? And the other two, of course, are mistaken. Then I end up with three allocations. One is correct and the other two are mistaken. Now, for x1, I can compute three benefits. NB x1 W1, but I can also compute NB x1 W2, and then NB, sorry, x1 W3. Perfect. And then I can take of these the minimum. Why I make this computation? Because I have a possible allocation x1. I'm not sure if it is true. So let me see, I'm not sure it is correct. So let me see what happens if I decide for x1. And I have three possible outcomes, three possible benefits. Because I have three different vectors of parameters, and I don't know which one is true. So, given that I have three possible outcomes for the benefit, if I want to be very prudent, let me compute the minimum. Because I'm sure that at least I have this amount of money available at the end of the story. But x1 is just one possibility. Now let me explore x2. Again, x2, I have three possible benefits. NB, x1, x2, sorry, W1, and then I have NB, x2, W2, and then I have NB, x3, W3, sorry, 2, W3. And then again, let me compute the minimum. And then I have x3 again. Let me compute NB x3 W1, and then let me compute NB x3 W2, and then NB x3 W3. And then let me take the minimum. Okay, so which decision should I take here? x1, x2, or x3? Okay, let me take the decision that gives to me the max of this minimum. Because in this way, I am sure to get the maximum of the minimum benefit. I am sure to get the maximum benefit that it's for sure available. I mean, I say again, the maximum benefit that is for sure available. This is the criteria of the maximum of the minimum. Of course, it is very prudential.
We will have this max for sure, because, for instance, if the first scenario is the max minimum, but then the second occurs, it means that it's lower than our estimated one, so it's not available.
No, I mean, if you decide x1, you have three alternatives, and let me compute the minimum. So it means that if you go with this decision x1, this is for sure available. But this is not the only possible decision. Let me try the second one. And the second one leads to a benefit that is for sure available, but it's not the same. And it may be lower or may be upper. Given that with x1, this minimum is for sure available if I decide x1, and given that if I decide x2, this minimum is for sure available, then let's take the decision with the maximum of the for sure. Okay, it's clear? And this is, yeah.
Why do you have for sure available?
Because I said that you have only three possible outcomes for the parameters. So one of them is correct.
Okay.
So if I decide for x1, and x1 may be the optimal allocation for w1, but it could be also a generic value. If you decide for a generic value, you have only three possible outcomes for the benefit. One of them occurs. One of them occurs. So if you take the minimum of the benefit, given that, I mean, one of these three benefits occurs, but you don't know what is the one. So if you take the maximum may happen with probability 1/3.